Moving to question number 12 now. Read the question. Two uniformly large parallel thin plates having charge densities plus sigma and minus sigma are kept in the XZ plane at a distance d apart. XZ plane means what? There are three coordinate axes, right? X, Y, Z. They are mutually perpendicular, right? X, Y, Z. Look at this. This is x-axis, this is y-axis, and this is z-axis, right? X-axis, y-axis, z-axis. XZ plane means it is nothing but the floor of your room. All right. This is x to the right, and z-axis is coming out of the board. Am I correct? So in the XZ plane, you are holding two sheets parallelly, as per the question. Okay. Can you read it again? There is this plane, XZ plane, and you're keeping what? Two sheets with charge densities plus sigma and minus sigma. Now sketch an equipotential surface due to electric field between the plates. We have to sketch an equipotential surface. Plus, there is another question. If a particle of mass m and charge minus q remains stationary between the plates, what is the magnitude and direction of electric field? I'll illustrate the question here. Look at this. Imagine we have two thin sheets. Look at this. This is the thin sheet here. All right. I'm taking a thin sheet right here in XZ plane. All right. And I have another thin sheet here in the same plane, XZ plane. Okay. I have the thin sheet here. Right. I have the thin sheet here. Right. I have two thin sheets kept like this. Okay, the one on top has positive charges. Why is it having positive charges? Because they say one plate has a surface charge density plus sigma, right? The other one is having what? Minus sigma. Yes, very good. Right. So the charges on this are all negative. Okay. So basically it looks like this. The roof of the room has positive charges and the floor has negative charges. Okay. So this is the setup they are trying to illustrate. Got it? And then how do we draw the electric field lines? Electric field lines are supposed to originate from positive, terminate on negative. So they must start from positive and they must end on negative. So I'm drawing the electric field lines from positive to negative. Look at that. Positive to negative, right. So I'll draw many of them, positive to negative. All right. Now positive, negative, the field lines are from positive to negative, this way. So basically it is like, just imagine raindrops are falling down. So the electric field lines are what? Electric field lines are coming straight from the top to bottom like this. Okay. So hope you understood this part. If you look at it, on top there is a plate with positive charges. And at the bottom there is another plate with negative charges. Got it? And electric field lines are from positive to negative. It is downward. They are asking you to sketch an equipotential surface. This is what kind of electric field? Uniform electric field, right? Because all the lines are parallel, all the lines are equally spaced. Such a field is called uniform electric field. We learned different shapes for equipotential surfaces. For a point charge, spherical surface. For uniform electric field, yes. For uniform electric field, a surface held perpendicular is equipotential. Okay. For a uniform electric field, a surface, any surface held perpendicularly is an equipotential surface. Right. So for this one, these are my field lines. I must draw something perpendicular to it. So I must hold something perpendicular to it. Am I correct? Correct. Electric field lines are coming straight down and this must be perpendicular. Equipotential surface must be perpendicular. I'll draw it now. Look at this. So this is going to be my equipotential surface. I can draw it right here in between. I can draw it right here. Got it? So that surface is where? That surface is right in between the plates. First plate is on top. Second plate is at the bottom. Then in between, I'm holding a surface. Now I'll just shade the surface. This is my equipotential surface. Okay, equipotential surface. So that answers the first part of the question. Now in the second part, they are saying something else. You are keeping a charge stationary in the middle. Do you remember having heard something like that? Millikan's oil drop experiment. How do you keep an oil drop in space? Imagine you keep an oil drop here. Now that will definitely fall down. Why is it falling down? Because gravity. Yes, gravity is pulling it down. Do you remember? All right. So if you put a drop here, it is falling down because gravity is pulling it down. Gravity is acting on it. mg is acting on it. It is called weight. All right. So imagine you are placing a charge here, right in the middle. You are placing a charge in the middle like this. This is my charge. Okay. Right here, I'm keeping the charge. Okay. And they say it is having negative charges, minus q, minus q, minus q, minus q. Tell me what the directions are. I have the electrostat, I have the gravitational force. The weight acting on this drop. Where is the weight acting? Weight always acts downwards, right? Weight always acts downwards, mg. Now, if that force can be nullified, if that force can be balanced, it can stay stationary. They're asking about what? They're saying about what? Keeping this charge stationary in space. So this charge is to be stationary. Look at this pen. If I drop it, it is falling down. But if it is to float, tell me what? The downward force must be cancelled by an upward force. Right. So here the downward force is gravity. Who is the upward force? Negative plate repels negative up. Positive plate attracts positive up, negative up. So together, the electrostatic force on this will be what? In the upward direction. It is called QE. Got it? It is called QE. So there are two forces. Do you remember electrostatic force? Yes. Equation for electrostatic force, we wrote it already. Tell me, that is F is equal to QE. So just imagine the scenario where the weight of this charge, which is mg, is balanced by the electrostatic force. Then the forces are cancelled. It can stay stationary, can stay afloat. Am I correct? So they're asking you to find the magnitude of electric field. What is electric field now? mg divided by q. That is second part of the question. There is one more thing. They are asking the direction of electric field also. How to say the direction of electric field? Always from positive to negative. Direction of electric field is, by convention, it is always from positive to negative. Correct. Positive is on top, negative is at the bottom. So you can say direction is from where to where? Top to bottom, top to bottom. Or you could say it is simply downward. Okay, electric field is acting downward. So there are three questions here. First question is to draw the equipotential surface. How do we draw the equipotential surface? First, you have to keep the sheets in the plane. Then what? Then you have to draw the electric field lines. Then we know what? Equipotential surface is always perpendicular to the electric field, uniform electric field, right? So right in between, you can keep a surface like this, which is perpendicular to the field lines. That will be equipotential. So this green surface is equipotential surface. Got it? And second part is asking you the conditions for keeping a charge stationary, charge particle stationary in between. What is the condition? You can say the charge, the force acting, the gravity acting on it is mg. That has to be cancelled by some other force. Here it is electrostatic force. So electrostatic force is acting upward. All right. mg is acting downward. Electrostatic force is acting upward. Okay. Because negative plate is repelling negative up. Positive plate is attracting negative up. So mg is equal to QE, and you can find out E using this equation, mg divided by Q. This is the magnitude of electric field. And again, direction is from where to where? Positive charge to negative charge. It is from top to bottom. Or you could say it is downward. Clear? Shall we write now?
Yes.
Yeah.